So, today we are going to see what are the different sources of losses. So, whenever we design any components or circuit at millimeter wave frequency, so we have to be very careful about the losses and monomode bandwidth. So, this monomode bandwidth we will see later how we define and what is it. So, let us start with what are the sources of losses. So, last day we have seen that if we have a transmission line which supports TEM wave. So, in that case the propagation constant it becomes a complex quantity gamma, this is equal to alpha plus j beta, and if we can determine the scattering parameter S11 and S21 of a given guiding structure. So, in that case we can calculate alpha the attenuation constant and beta the phase constant of any given guiding structure. So, now let us see what are the sources of losses. So, we have mainly three different sources of losses: dielectric loss, conductor loss, and the radiation and surface wave loss. So, dielectric loss, why it happens? So, whenever any electromagnetic wave propagates through any dielectric medium or any insulating medium, in that case the molecules of any dielectric layer it behaves as dipole. Now, we have thermal noise. So, due to thermal noise the orientation of these dipoles are in random direction. So, when electromagnetic wave propagates through this medium, then this dipole they try to orient itself. So, in that procedure it absorbs some amount of energy. So, and finally, it will give us some heat. So, it is a loss to the propagating electromagnetic wave. So, how we quantify this loss? So, instead of the simple dielectric constant epsilon r, we represent dielectric constant by a complex number. So, we can see the permittivity in general, it has one real component epsilon dashed and one imaginary component j epsilon double dashed. Intentionally we are using one negative sign here, so that loss it becomes a positive quantity. Now, let us consider the any monochromatic plane wave is propagating through this dielectric medium. So, in that case if it is linearly polarized, so electric field E it can be written as E naught into e to the power j omega t. Now, let us use the Maxwell's curl equation, curl H equal to j plus del d del t. So, let us solve it and let us see what happen. So, curl H, this is equal to the conduction current component J C plus del d del t. D is the displacement vector. So, this is equal to epsilon E. So, where epsilon it is a complex quantity, it can be given by epsilon dashed minus j epsilon double dashed. So, the conduction current quantity it is related to the applied electric field as sigma into E, where sigma is the conductivity of the medium. So, since we are considering a dielectric medium, sigma is negligibly small, we can also consider sigma as 0. So, plus del del t of, so we have epsilon, so epsilon dashed minus j epsilon double dashed E. So, it comes sigma E plus we have omega epsilon double dashed E plus the imaginary quantity j omega epsilon dashed E. So, because of this real quantity sigma, we know that this medium will behave as a lossy medium. Now, we see the imaginary quantity epsilon dashed. So, in the final expression it will add up to this real quantity. So, then together this is sigma plus omega epsilon double dash E, and the imaginary quantity we have j omega epsilon dash E. So, this first part we can call it the conduction current component J C, and the second part we can call it the displacement current component J D. Now, if we represent it using vector diagram, then J C it is along the real axis and J D this is along the imaginary axis. Then the overall current component J, it makes an angle with the displacement current component, and this angle tangent it can be given by J C by J D. So, or if I put the values, it comes omega epsilon double dash plus sigma divided by epsilon dash. So, this is called the loss tangent of this dielectric medium. Since we are considering dielectric, we can assume sigma is 0, then this quantity is approximately, we can write down epsilon double dash divided by epsilon dash. Now, let us go back to our slide. So, in general, then electric loss tangent tan delta, it is defined as the lossy reaction by lossless reaction, and which we see equal to omega epsilon double dash plus sigma divided by omega epsilon dash. So, if I plot loss tangent versus frequency, so what do you think, it will increase or decrease? So, above we have sigma plus omega epsilon double dash. So, it should decrease with frequency, but in last lectures we have seen the, some measured loss tangent values at different frequencies. So, measured value usually we have seen it increases with frequency. So, similarly, we can define magnetic loss tangent. The procedure is very similar, and we will represent in this case tan delta m. This is equal to mu double dash by mu dash, but most of the materials are not magnetically susceptible. So, we can simply neglect this tan delta m part for most of the materials, unless we are considering materials like ferrites, iron or nickel. Now, if I consider a microstrip line or CPW lines, so we have to fabricate them on some dielectric substrate. So, obviously, it will be associated with some dielectric loss. We have a closed form expression for that. So, the dielectric loss per unit length for these two lines alpha d, that is equal to approximately 2.73 multiplied by this factor. So, it depends on tan delta, but as well as frequency, because we have one term lambda naught here, and if we increase frequency lambda naught, it will decrease. So, if it decreases as a whole alpha d, it will increase. So, we see that for CPW line and microstrip line, dielectric loss it increases with frequency, as the closed form expression says. Next is conductor loss, that is another important factor. So, this represents the Joule heating. Now, if we have a TEM line, so that means a wave guiding structure that is supporting transverse electromagnetic wave. So, in that case, we can actually theoretically calculate what is the attenuation constant due to conductor loss alpha c. So, alpha c in this case, this is equal to beta into delta s by 4 z naught into DTL of z naught. Z naught, this is the characteristics impedance of the transmission line. Delta s, this is the skin depth. So, we can represent delta s in terms of surface resistance as shown here. R s, this is equal to square root of omega mu naught by twice sigma, that is equal to 1 by sigma delta s, and this ddl of z naught, it represents change in z naught if all the metal parts are reduced by delta L. So, for example, if we have a coaxial cable, let us say it is excited in TEM mode. So, in that case we have to first calculate what is the characteristics impedance of a given coaxial cable, and then what we will be doing. So, we will reduce inner conductors as well as we will increase the diameter of outer conductor by delta L, and we will recalculate what is the new z naught value. So, that will give you then delta z naught, then we can easily calculate delta L or ddl of z naught. So, we can calculate alpha c for that given coaxial cable. Now, when we calculate alpha c using this formula, we made one important assumption. What is that assumption? That the metal surface is smooth. So, there is no roughness on the metal surface, but if we look at practical metal surface, it has some roughness. Due to this roughness, loss further increases. So, we have again one more closed form expression. So, this is given below. So, let us say the surface roughness we are defining by capital delta, and it represents the RMS value of surface roughness. Then the corrected attenuation constant for a rough surface alpha c dashed, this is equal to alpha c multiplied by 1 plus we have a correction factor here. So, 2 by pi tan inverse 1.4 into capital delta by small delta is whole squared. So, small delta is, this is the skin depth of that metal. So, we see then actual alpha c, it will be much more compared to what we calculated previously, and it also increases with this capital delta. So, for a rougher surface, then we have more conductor loss. So, let us take one example. So, before that, you see in this picture, top left picture, so it shows electrodeposited copper zoom in view, at least 100 times zoom in view. So, here typical surface roughness is 0.5 to 0.35 micrometer. Now, you compare this value with the skin depth. Do you remember what is the skin depth value for copper at 100 gigahertz? It is 0.21 micrometer. So, if I compare this value, this capital delta, it is already more than delta S skin depth. So, surface roughness will be very high. Due to the surface roughness, we have a very high conductor loss than what we calculated. So, this type of copper is used to make that PCB, printed circuit board. So, if you take a close photograph of any printed circuit board from top, you can see the copper is looking like this. So, now it when the companies, they fabricate these printed circuit boards, they follow actually different fabrication procedure. So, this is for the electrodeposited copper. We have also rolled copper. So, for rolled copper, the surface roughness is little smaller. So, then another important observation we have, that when we are going to order our substrate to design millimeter wave components, so in that case we have to also look at the surface roughness value. So, if the surface roughness is very high, then we will be expecting high conductor loss. So, at least you look at the value, it should be much smaller compared to the skin depth value when you choose your substrate. So, be careful about that. So, another example we will take. So, here we are, what we are doing, we are plotting the attenuation loss alpha, this represents the conductor loss only, versus frequency for a standard rectangular waveguide WR10, it is air field. So, if I consider 0 surface roughness, then this bottommost line, it shows the variation of alpha c versus frequency. So, typical value is 2.2 to 2.3 dB per meter, and now these are all theoretically calculated values. If I increase delta value, let us say 0.25 to 1, so this is capital delta by small delta s. So, that means it represents the surface roughness with respect to the skin depth value at the midband frequency. So, we see that alpha c is increasing, and at lower end it can be as high as 2 times of the original value. So, the conclusion is then the effect of surface roughness, it changes actually alpha c. And now we see in gamma we have two quantities, alpha and beta. So, the effect of surface roughness on alpha is more prominent compared to beta. Next is radiation and surface wave loss. So, whenever we have any discontinuity in this structure, let us say we have some open ended stub or any metal dielectric discontinuity, or let us say you have dielectric air boundary in your structure, or it can be in any form. You have some impedance step in your circuit in your semi open structure, for example microstrip impedance step. So, it will radiate. Now, the amount of radiation obviously depends on the structure, and the direction of this radiation is in random direction. So, now for microstrip line or CPW line, always we will be having some fringing fields in air, but if we have any fringing field in air, that does not necessarily means it will radiate. The basic condition for radiation is that the electric field and magnetic field component which is in air, that should be in phase. Otherwise, if they are in phase quadrature, we have reactive components, reactive power, and the energy whatever we have, it will be stored in the near field. So, it will not radiate. So, if we have any EM solver or full wave simulator, we can simulate our structure, and actually we can calculate the radiation or amount of radiation coming out from our structure. This is very important from EMI EMC point of view. So, next one more example. If any transmission line or any other guiding structure, if it supports first wave, it is associated with radiation, and we last day we discussed that the structure, it will radiate continuously along its length. So, let us take one example. So, this figure, it shows a CPW line. So, this is the cross section of the CPW line. So, we have 3 strips, these are sitting on a dielectric slab. So, this is the central strip, and left and rightmost strips, they are used as the ground plane. Now, this configuration, it can be excited in even mode as well as it can be excited in odd mode. So, in even mode, if you look at the electric field plots, they starts from the signal line or the central line and terminates at the ground plane. So, we can say that both of these ground, left hand and right hand side strips, they are at same potential. Now, look at the right figure. So, this CPW line is excited in odd mode. Now, the electric field line, they starts from the rightmost ground and then again from signal to left ground. So, that means the rightmost ground, it is at higher potential compared to the leftmost ground, and in practice even mode, it is a slow wave and it is a guided components, guided mode. So, the desired mode is even mode, and odd mode, it will be radiated continuously along the line. So, it is undesired mode. So, what can be the remedy? We do not want this odd mode. So, if I look at these two figures, one important observation is that for even mode two ground planes they are at same potential, and in odd mode these two ground planes they are at different potential. So, practically what we do, we use bonding wire, simply copper wire, and that is soldered between the two extreme ground planes. Now, if I solder one copper wire between these two extreme ground planes, so we make it sure that two ground planes they are at same potential. So, we are forcing it by using external copper wire. So, that is a way how we can suppress odd mode excitation of CPW line. So, we have to use this copper wire in periodic nature. So, the periodicity it should be less than lambda g by 4, where lambda g is the guided wavelength in CPW line. So, next we will see that substrate, a dielectric slab simply, it can support wave propagation, and the problem with this type of wave propagation is that, so this is not just confined to any one particular channel, it will spread throughout the substrate, and we call these as the substrate modes or the surface wave modes. And this type of transmission line like CPW and microstrip line, they are fabricated on a dielectric slab, so they can easily excite the surface wave modes. And what is the problem of surface wave modes? Since it spreads throughout the substrate, so we will be having electromagnetic interference problem with the nearby circuit or crosstalk problem, and the power lost to the surface wave. So, it is a wastage to the transmission line, because we can't utilize this power. So, then the surface wave, particularly at very high frequency like at millimeter wave frequency, the effect is detrimental, and we have to study its effect very carefully, so that we can avoid it. So, before starting the surface wave modes in general, let us discuss about what are leaky wave modes and what are substrate wave modes, which is confined to the substrate. Let us say we have a dielectric slab as shown in this figure, and any wave somehow incident inside this dielectric, and this is incident on the dielectric air boundary with angle of incidence theta 1. Now, if this angle of incidence is smaller than the critical angle, then a part of this incident wave it will be transmitted to air, and another part is reflected back inside dielectric, and this it will continue throughout the substrate. So, as a whole, whatever this refracted components or transmitted component, it comes out as radiation from the structure, and we call it the leaky wave mode. It can be shown mathematically. It is possible only if the phase velocity of this wave is higher than C naught. So, that means in the case of a fast wave. So, this is a conceptual diagram. Next, the same wave, but in this case angle of incidence is more than the critical angle. So, the relationship for critical angle sin theta c, this is equal to 1 by root of epsilon r. Epsilon r is the dielectric constant of this slab. Now, since theta 1 is more than theta c, whole of this incident electromagnetic wave is reflected back. So, we have total reflection and it will continue. So, we see that a dielectric slab itself, it can behave as a guiding structure, and in this case mathematically it can be shown Vp is less than C. That means it is a slow wave scenario, and we do not have any significant radiation from this structure. So, in this case electromagnetic wave propagates through the dielectric slab, but what is the problem then? The problem is that it not only propagate in z direction, since the dielectric slab it is in xz plane. So, it will propagate in xz plane and it will spread throughout the substrate. So, we can't utilize this substrate wave mode or surface wave modes. So, let us learn about this surface wave mode in details. So, before that we need to know what are the different types of modes that can exist in any guiding structure. So, mainly we deal with three modes: TEM mode or transverse electromagnetic mode. So, by definition, in the direction of propagation it does not have any electric field or magnetic field component. Then we have transverse electric mode. In the direction of propagation we will not have any electric field component, and the third one is transverse magnetic mode. In addition to these, we have many hybrid modes. So, right now we are not discussing those modes. So, mainly we will deal with these three modes. So, let us first learn what are the characteristics of these three different modes. So, let us start with the TEM mode. So, we are considering a electromagnetic wave is propagating in z direction and it is linearly polarized. It has Uy components. So, by definition then z equal to 0 and Hz equal to 0, and beta it can be given as omega square root of mu epsilon, that is equal to k, and cut-off wave number kc, this is equal to square root of k square minus beta square, this is equal to 0. So, it is interesting to note that kc cut-off wave number is 0. So, that means it does not have any cut-off frequency. So, it can start propagation right from DC. The wave impedance Z for TEM line, it is how we define Ex by Hy, this is equal to square root of mu by epsilon, sometimes we call it eta. For TEM line we can calculate the characteristics impedance, since we can calculate the voltage and current for this. So, how we calculate current and voltage? Let us say we have a two-wire transmission line systems. Let me draw one diagram. So, if I draw the electric field components, this is the electric field lines, and the magnetic field lines, it will be perpendicular to it and it will encircle the conductor. So, this red part it shows the conductor, it can be of any shape. So, we see that electric field it starts from a conductor and it terminates in another conductor, and how to calculate the potential difference between these two. So, in that case we have to just define one line, let us say from point 1 to point 2. So, then what we do? So, V1 to this is equal to integration 1 to 2 E dot dl. So, this will give you the potential difference between these two or voltage difference. Now, how we can calculate current flowing through any single conductor? We have to consider one closed loop, and then the current component I, this is equal to closed integral H dot dl. So, we see that the electric field it should starts at some point and it should terminate at some point. So, that a potential difference can exist between these two. So, at least it will be a two conductor system or more than that, otherwise it can't support TEM or transverse electromagnetic wave. And in this case, since we can calculate voltage and current, then we can easily define characteristics impedance of the line, that is equal to V by I. So, this is only possible for TEM line. So, now we will take a short break and then we will continue with other different modes.